Cool. So you guys, we should have started now, and you will have access to this whenever you want. Thanks for guys for coming. I appreciate it. Um, so we've kind of like stumbled into this entirely new form of chemistry, right? Where suddenly like chemistry has all this math in it, right? It's really weird.
All of a
And
sudden.
like you're like, I wonder what's next. Is it more drawings of like, or like, like structures? It's like, no, it turns out it's a bunch of math. So that's what you're going to be doing for this semester, unfortunately. But we'll get through it. This is definitely the most math that you do in the semester, if that's any consolation. So
Yay.
yes,
Yes.
so this is the hump, this is the activation energy for us to finish this class. Okay, yes.
Nooch.
Let's do it. So okay, so we should probably start off with like doing some problems with determining the average rate of reactions. So let's start off with that. Okay, so given the following balanced equation, determine the rate of the reaction with respect to H2. So, okay, so we're with respect to H2. So hopefully you guys have this in front of you, by the way, so we can just work on it together. So how do I define the rate of the reaction with respect to one of my constituents of my reactant? So I'm hearing kind of an echo. I think I'm going to mute one of you guys to see if it goes away. So, all right, I think that might have been it. Cool. But if you have a question, unmute yourself at any point and just talk. Okay. Okay. So if we're determining the rate of the reaction, we need to remember the fact that we can always define the rate of the reaction by each of these components here. And the way we do that is through this particular concept where we said there's the rate of the reaction, the way we define it is the change in concentration with respect to some change in time. So the change in brackets, usually concentration, and I normally plug something in there like a reactant or a product. And just to kind of flesh that out, that just means it's your final concentration minus your initial concentration over your T final minus your T initial. Yep. And in the case of like a basic reaction where it's like A goes to B, then it would be A final, and so on. And I would plug in A, Now, it turns out that the way we like to define this is that we like to set all of, I can do this for every one of these guys. I can do it for this first one, the second one, and this third one, and I can set them all equal to each other. And the way that I do that is that I want to express the rate with respect to 1 mole of everything. So can anybody tell me what they think the answer would be for this first one, and can you explain yourself?
E.
I think that it's D.
Okay, yeah.
It's D.
Awesome, yeah. So can you explain, one of you guys pick it up, explain why?
Yeah. So first of all, when you are looking at the reactants, they have to have a negative
Yes.
on the beginning, like on the front of the whole equation.
Yes.
And also the way that you can tell that it's that answer is because you always do the number in front of the reactant on the bottom, so like
Yeah.
1/3. And yes, I think that would be my...
Exactly, yeah. So the first thing is that negative is there, so that's good because we're talking about a reactant, H2. So that's a reactant on the left side of the arrow. So it's negative. And then we accommodate for the coefficient by dividing by the coefficient with respect to our rate, right? So then that means then, yeah, our answer would be D in this case, yeah. Pretty straightforward question, I think. And yeah, the hardest thing I think here is just that occasionally professors get sneaky and they don't include the negative and they'll have the same rate above it, and you might mistakenly click 1/3, if it was a positive instead, and you might mistakenly forget that it does need to have that negative in front of it. Okay, so be careful. Yeah, pretty easy question I think so far. All right, write a balanced reaction for which the following rate relationships are true. So if we're given this rate equation like this, can we come back and determine the chemical equation? Okay, I'm going to give you guys like 10 seconds to choose an answer, and then we'll talk about it after. Okay. All right, let's do it. So who has an answer they think is right?
I think it's A.
I think it's A.
B.
I think
Yes, I agree.
I think I would agree with you. Yeah, I think I would agree with you. So we can remember we can always define reactants by the negative sign, right? And I don't see any other negatives here or here. So that means that N2O5 is our reactant. So we have N2O5, sorry, and then you have an arrow because there's no other negatives. And then we see then, remember that the fractions that we see
I'm done.
represent the coefficients. So that means that's a 1/2, so that becomes a 2, and that's NO2 and O2. And that would be A in this case. Yep, that's exactly right. Good job. Remember, I could have like swapped those things, right? So it could have been the minus 1/2 at the end, right? It could have been like over here. And remember that it just so happened that it happened to be in the right order, but it could have been flipped. These are just equality signs, right? So don't get too comfortable with the order being the right formula, if that makes sense. Cool. Hopefully that makes sense for everybody. Alrighty. And then moving on to kind of our last part of this section. I think the section was pretty straightforward, but now let's do this last one. We're actually doing some numbers in here. Given the following balanced equation, determine the rate of the reaction with respect to NOCl. So that's what we're trying to figure out. The rate of the reaction with respect to NOCl. If the rate of Cl2 loss is that number that we see there, what is the rate of formation of NOCl? Okay, so what do you guys think? How do we solve this problem? I'm going to give you like maybe like 30 seconds to work on it yourself, and then we'll come back and talk about it. Okay. I'm going to pause the recording, and then I can return it so people don't have to watch us kind of looking at our screens. I'm probably not going to do that very much because that noise is super annoying. Okay, so do you guys have a chance to work on the problem?
I got D.
Okay, cool. So we have one person that's saying D. Anybody else?
Yeah, I got D2.
Okay, cool. So how did you solve the problem?
Um,
I use the
so
stoichiometric coefficient of NOCl to help me figure out that it is 2 times faster than the loss of Cl2, since for every mole of Cl2 loss, there are 2 moles of NOCl gained.
Yeah, so yeah, that's cool. So quantitatively, what we can do is we could do something like this. We could say that the change in concentration of Cl2 with respect to time, the negative change of that, because it's a reactant, is equal to the change in concentration, I put a coefficient, 1/2 the change in concentration of NOCl with respect to time. Yeah?
Mm-hmm.
And then we're asking for the rate of formation with respect to NOCl, right? So what I want is just this, right? So I need to isolate just that. And the way I do that is by multiplying both sides by 2, and that will get rid of that 1/2 there. So multiplying both sides by 2. That will cancel here. And then I just have to get 2 times that 4.84, and I'll get my answer. And if you do that, you'll get the answer, which is equal to 9.68 times 10 to the minus 2. Good job. So that's the answer. So D. Good job. So that's how you do it like quantitatively. But you can see, though, by looking at the equation that you can just say, because there's a coefficient of 2 in front of my NOCl, this is kind of what Alex was saying. He's saying that that means that it's forming at twice the rate at which I'm losing Cl2. That's kind of a mouthful, but that's the idea. And that's why he got it like quick, if that makes sense. Cool. So let's move on. Does that make sense for everybody?
Yes, I like numbers too.
Cool. Yeah. So the numbers, I'm kind of like I'm an overthinker, like a chronic overthinker. So like if I like analyze it like that, I'll screw up. So I'm a big numbers guy. So I like showing equations. So that's why I do it like that. Oh, I should probably write my answer. So the change in NOCl with respect to time is equal to that. Cool. Awesome. So then I also encourage you to do there's a lot of problems you can do that are on the review sheet for problems like this if you feel like you need more practice. And if you do need even more, if this is a concept that doesn't make sense to you for people watching or anybody here, just contact me directly and I could pick some problems from the textbook that I think will be good for you. So that's the case for anything. If you ever like, hey, I kind of suck at these problems, let me know and then I'll find problems for you. Okay. Then the next sections that we're going to talk about, we're going to be utilizing this chart right here, which is the rate loss summary chart. Now, when I took this class, um, I made myself like a pledge that I would never use a cheat sheet for this class because it made it so I was like forced to know the material here. Now we're in this like weird online environment, so I'm pretty sure you'll have access to these things like this in front of you, um, on like a cheat sheet or something. So if you want, you can just have this in front of you and know how to use it, or you can memorize it and all these problems will be a breeze really if you know it that well. Okay. Um, so it has been very helpful. And if you plan on going into like biochem, you will see that your hard work in memorizing it was useful after all. So that's an option too. Okay. All right. So how do we look at this stuff, right? Well, it's remember that, and these are kind of like our kind of like canonical orders, like 0, 1, and 2. There are other orders that exist, but like half orders, right? We talked about, or negative order and -1 order. But these three that we see here are kind of the ones that you're responsible for with respect to knowing the equations for, if that makes sense. That's not to say that you may not encounter a negative order or a square root of 2, order, you know what I mean?
Yeah.
But you do need to know the equations for these three, okay? And in respect, because you know the equations of these three, the integrated rate laws, remember that these can be plotted on a graph, and you also need to know the graphs that correspond with them, okay? In particular, you should be very careful with the slopes. So you should know that the slopes and the axes. So the axes and the slope tell you what type of order it is. So sometimes you'll get problems where you'll only get graphs and you have to figure out what order it is, and you can determine that by the axes and the slope. So you can see why it's really important that you know what graphs correspond with what order. Does that make sense for everybody?
Yes.
Cool. All right. So we will be consulting this for the rest of the workshop. So it's here, and then you can always just flip to it or scroll up if you downloaded it, okay? All right. Let's do some conceptual questions. Give the characteristic of a first order reaction having only one reactant. Okay, I'm going to give you guys a second to read this, okay? So I'll give you like 15 seconds to maybe formulate an answer, okay? So you go ahead. Hmm. All right. Do you guys have a chance to read your the things?
Yes.
All right. What do you guys think?
I thought of E.
Yeah, I thought it was E too.
Okay. Cool. Yeah. So let's figure this out, right? Okay. So we're talking about a first order reaction, right? So we're talking about this next one here, right? Okay. So the rate of the reaction, right? If we look at that, if we look at all of our equations, right? Like let's say you didn't know how to do this at all, right? The only equation that actually contains rate in it is which one? It's that first one, right? The rate law equation, right?
Mhm.
And the first one says that the rate is equal to Ka to the first one, to the first power. So rate is equal to Ka to the first power, right? And that means that what? If I increase A, my rate goes up. If I decrease A, my rate goes down. That means there's a direct proportionality between my rate and my concentration of my reactant. So yes, that's exactly right. The answer is E in this case.
Hooray.
That's absolutely right. It's directly proportional, right? Um, as opposed to what? A second order would be what? The rate is proportional to the square of the concentration of the reactant, right? If it was second order.
Yes.
So a second order, let's just do a little side note. The rate, let's say rate 2, right, is equal to K A squared, right? So then my rate is proportional to the square of the concentration of my reactant, right? And then conversely, my rate 0, right, it would be K A to the 0 power, right? Right? And then A to the 0 is what?
Uh,
What's
K-
any
One?
number? Yeah, any
One?
number raised to the 0 power is 1, right?
1.
So that's equal to just K then, isn't it?
Mm-hmm.
So then is my, with a 0 order, is my rate proportional to my concentration? It's not, right? It's not even in the equation, right? You can increase the concentration of A until the cows come home, but the rate is not going to change, if that makes sense.
Yeah.
Because there's no A term right here, right?
Mm-hmm.
So with a first order, it's directly proportional. With a second order, it's proportional to the square. And with a 0 order, it's not proportional to concentration at all. Does that make sense?
Yes.
Awesome. Cool. So this is just some like wordy sentences that hopefully are getting into your brain, because like I can't ask every multiple choice question, you know? So he can
Mm-hmm.
ask any of these, and I want to make sure that you've like seen at least some of these. Okay. All right. So what are the units of K in a 0 order reaction? I'm going to give you guys like 30 seconds to work it out. You let me know, okay? It's a big difference, huh, with like somebody writing stuff versus a PowerPoint, huh?
Yes, this is so much better.
Yeah, I think this is a good form of learning it.
It's crazy. Like yeah, my classes that actually write things, it's like, oh my god, I love it. Versus like PowerPoints, I can't. All right, let's do it. So then remember, the way we're going to do this is with rate laws, right? So rate is equal to, we'll just use A because we keep using A, right? And then remember that in front of that A term, there's usually there's a constant here, that rate constant. There we go. So if it's a 0 order, then it has a 0 on top like that. Now, what are the units for rate typically?
Molar per second.
Molar per second, right? Yeah. So the units of rate are always molar per second. Okay. Yeah, molarity per second. Okay. Don't forget that. And that will always allow you to determine the units for K. So then because the A term cancels out and turns into 1, then I can replace rate with molar per second, and that tells me my units for K.
Mm.
Okay, so my units for K are molar per second. Is that cool with everybody?
Yes.
So then A is my answer in this case. All right, let's do this next one. It's going to give us a little bit more like mathematical problems, but we'll figure it out. We'll do it, okay? So what are the units of K with the following rate law? Notice we have another term now, so we need to consider that, okay? Alrighty, so then I'll give you guys like 30 seconds to work on it, okay? ba. You guys ready?
I think so.
Oh, if you can't like talk, you can utilize your little thumb thing if you want. I think you can just hit little thumbs up or some stuff like that. That'll like communicate to me that you guys are good too. If you don't want to unmute your mic.
You
Okay,
still hearing the echo?
a little bit. I think it's just because the speakers are loud.
I'm gonna turn mine a little bit down, see if this helps.
Okay. All right. So what are the units of k in the following rate law? Yeah, I still hear an echo.
Okay.
Okay. So then the way we solve this problem is that we need to remember that the rate is always in units of molar per second, right? And there's this k here. Now, what do the brackets mean again?
The concentration of the reactants or
Yeah, and or concentration in terms of what type of unit?
moles?
Mol,
Polarity.
molarity, yeah.
Molarity, yeah.
Molarity, yeah, which is equal to capital M also. So if there's, in this case, you can think of it like a molarity times molarity, right? Then my answer here then is molar per second equals molarity squared, kind of, right? Okay, I'm gonna get rid of the brackets for simplicity, but just so I don't have to write them anymore. Okay, so then we need to isolate K, right? So we divide both sides by molar squared. Are we cool with that? These will cancel. And then I only have one molar here, that'll be gone. And then one of these molars will be gone here. So then my answer is equal to, let's see, that's K is equal to 1 over seconds times molarity. That can also be written as what? That's also written as K is equal to seconds to the -1 times molarity to the -1. So my answer in this case is C. A little complicated, right?
Yeah.
Do you guys feel comfortable with that, or should I make another example?
I feel like the way I figured it out was using the table because I
Yeah,
got C and the rate, I used the order 2, and I thought
that's really
maybe,
good thinking. That's good thinking. Yeah. So you can look at this, right, and you can say, well, this is really great. I'm glad you brought it up. So then, because each of these has an order of 1 and 1, then the overall rate order for the entire reaction is order 2. So then we can then just look at our rate order 2, and we could say, oh, what are the units for a rate order 2? Boom. Cool. That's a really good point. I like that a lot. Now, that's really cool. So then, but what if we got like a rate order 3 though? How would you do it, right? Well, then you'd have to use the other method, right? Is that okay with you guys?
yeah.
Cool. So hopefully you guys are cool with how I did that. Maybe it might be worth doing one more example where you do one where it's something like rate equals k a to the squared b to the you can even get really fancy with this. It's basically an algebra problem at that point. Yeah, you could do something like that. And in which case you have to consider the a to the third power, and you'll figure it out. But yeah, so maybe try working on stuff like that. We can talk later if you have any extra questions, and we can work on that. Okay, if you want more practice. All right. So, I kind of gave away this answer by doing this, but what is the overall order of the following reaction given the rate law that we see right here? So because, like I said earlier, with that good point that was mentioned before, you can solve for the overall rate order is equal to the sum of each individual order. So I mean like that 1 and that 2, right? So what's my overall order in this case? It would be a third order reaction. That would be that. Okay. Awesome. So hopefully that makes sense. Occasionally you get like fractions as your orders. So you have to just remember how to add fractions. That's another thing that happens as well. Okay. Cool. So is everybody cool with that? Any questions?
Go.
Cool. Hopefully you guys are all doing good. Okay. I'm gonna give you guys another like 30 seconds to, I'm gonna give you like I'll give you a minute to do the first and second problem that I have on the screen right now, okay? So I'll give you a minute from 3:39, so you can get started on that. Okay, how do you guys feel? Ready? I'm ready. Ready to take on the world. Let's do it. So given the following rate law, how does the rate change if the concentration of Y is doubled, right? So what's the order of Y? Well, because of that order right there that we see, it's a second order. So how would the rate change if I double Y? Well, then that will, if we plugged in a 2 in here, then that would raise it by a factor of 2 squared, which is equal to raising it by a factor of 4. So my answer in this case would be B. Okay. Everybody else get that answer?
Yes.
Cool. Awesome. And then given the following rate law, how does the rate of the reaction change if the concentration of Y is doubled? So Y is a third order, right? So we have to imagine plugging in the factor into that. So that would be by raising it by a factor of 2 to the third power, which is equal to 2 times 2 times 2, which is equal to 8. So it rose it by a factor of 8. Right? And then like Fenton was telling me earlier, occasionally people get kind of stuck with the idea of it only being doubled, the concentration being doubled. He could plug in any concentration change that he wants in there. So it doesn't necessarily mean that he doubles it. He could quadruple the concentration. And if he did that, we'd have to raise it 4 to the third power and so on, if that makes sense. So don't get too tied on the idea of it being 2 to some power. Focus more on the concept, which is that you're raising the factor of which you're changing the concentration by the order, if that makes sense. Okay, so hopefully this is all super boring and easy, because that means that we're in a good spot. That's what I want, ideally. Okay. So now that we have an idea, we have kind of a grasp on how to deal with rate laws, right? We know how to implement them, and we know what the rate orders, how they affect the rate overall, right? The reaction orders. Now we need to figure out how do we actually determine them. And to do that, we need to do them experimentally. Okay? We always determine rate orders or reaction orders experimentally. We need data to figure them out. And don't let anybody tell you different, okay? So how do we do that? There's a couple ways that people do it. Actually, show of hands, how comfortable are you guys with getting these?
Decent.
You feel good?
I want to say pretty comfortable.
Okay. And then I can move pretty quick then through it. Everybody else cool with that? Yeah? And get to some harder stuff. These first two are kind of like warm up, and this third one, the red one, is the one I want to really get to. Okay. So we'll get to that. So let's do the first problem. Determine the rate law and the value of K for the following reaction using the data provided. All right. So we need to find out the rate law. And then notice that there's numbers in front of this too. So those are we're also solving for K then. So let's do this. So we can see here that from here to here, it was constant, right? This concentration was constant. Whereas what's the factor by which I changed from 0.4 to 0.8? That's doubling, right? That's doubling the concentration of Cl2. So then what that means then is that I can then analyze the rate and see how that changed. So let's see that. Well, 1.97, I'll show you the math on how I do that, okay? So it's gonna be rate 2 over rate 1 is equal to K CO to some power M and Cl2 to some power N. Like I said, I'm kind of a math guy. Okay. And it looks like because we kept CO constant, that these terms will cancel. And also, assuming we're keeping the same temperature, the K's will also cancel. So then our equation kind of simplifies a bit to R2 over R1, which is R standing for rate in this case. And what's our first number? Our rate 2 is going to be 1.97 raised to the n power, and 0.696 raised to the n power. Okay. And we found out that R2 over R1, I'm sorry, I fucked that up. I'm punching this in wrong. Sorry, that's 0.80 and 0.40. Apologize. That's the concentration at time 2 over concentration at time 1. And then we found out right here, R2 over R1, that's going to be 1.97 over 0.696. Okay. We can do that answer really quick. 1.97 divided by 0.696. Did you guys see how you guys got a weird answer for that, right? So what did you get for 1.97 over 0.696 when you typed it in? Well, if you did it, you'd find out that you got something like 2.83, right? And we said that if we do this, it's 0.80 over 0.40 to the n power. Turns out I can combine those into one thing, and you get something that looks kind of like 2 to the n power like that, right? So do you guys see how this was kind of a harder problem in disguise, right? So do you guys have an idea of what we can do next?
This is where the logs come in.
That's where the logs come in. that cracks me up. That's hilarious. This is where the logs come in, yeah. Because, you know, it turns out that not every one of these questions is going to be like super simple, like, oh, it's first, second, or third order, right? It could also be some gross order, right? I mean, look at these options here. We have like 2.8 as an order here. You see that thing? It's gross. So here's what we're going to do. We're going to have to solve for n. And we have to do that using some algebra, unfortunately. So we do that by getting, we'll just do the natural log of both sides. Hey, Alex, getting your natural log practice in.
Here we go.
Real quick, too. We got that really quick. So all I did was I got the natural log of both sides. And we need to remember a really fancy rule about logs, that the natural log of x to the a can be rewritten as a to the ln of x. So all that's saying is that if you ever have a number that's raised to a power, you can pull that power in front of the natural log and still get the same number. Cool. I'm just grabbing that and putting it over here. Cool. These two are equivalent statements, which then that allows us to solve for n, right? Because we can say the ln of 2.83 is equal to n times the ln of 2. And then we can divide both sides by the natural log of 2. And then we can get our n. N is equal to, we could just punch that in. If you do the natural log of 2.83 divided by the natural log of 2, what do you get? You get 1.5. Okay, so which of these answers here has a 1.5? Well, there's none of them that have 1.5, but if you remember that 1.5 is equivalent to 3 over 2. Whew, kind of a hard one, huh?
Yeah.
How do you guys, Martha, Tiff, and Lofber, how do you guys feel about this one?
I think I need more practice on this one.
Yeah,
Yeah,
I feel
same.
Yeah,
it
you're like,
was-
I totally got this, and it's like, whoa, what the fuck? Yeah, it's crazy, right?
I'm writing notes on it, but at the end where so where it's written in red where the ln is right there, you put a in the front, right?
Yeah.
So I kind of got lost right there where
That's pretty good. You got like 80% of the way then. That's like really good.
I'm kind of lost on the end though. So you take 2.83 and then you divide it by ln. But why do you divide it by ln of?
So the whole goal of this whole thing is to solve for n, right? Because n is my reaction order. Does that make sense?
Yes.
So that's what I want to solve for, and I'm literally solving for n, but algebraically. Normally, the way Fenton teaches that, he's teaching you like, yeah, you can look at the relationship between these rates and concentrations and you can figure it out. But like that doesn't work if it's not a normal reaction. Yeah, and what I'm teaching you here is like, yeah, what if it's gross, right? What if it's a gross reaction order? How are you going to do it, right? Well, you can do it this way, right? You could solve it numerically. Fortunately, I think the other one is actually pretty easy to solve for. So let's do that one instead. Hopefully that will get us to like understand this conceptually. So let's look at another reaction, right? So far we solved for n. So now we know that the n is equal to 3/2, right? So that means that we know that Cl2 is raised to the 3/2. Is that okay? But we still don't know what CO is raised to. That's raised to some factor m. Is that okay with everybody?
Yes.
Okay, so
Yeah.
we need to then look at a reaction where CO is held constant. I'm sorry, where Cl2 is held constant, but CO changes. So then let's look at that.
2 and 3.
So that would be here. This is constant, right?
I have a quick question.
Yeah.
So yeah, how you when you did the first two, rate 1 and rate 2, and then you started to flip it, doing the numbers, rate 2 to rate 1. Are you always going to do it like that when you're comparing?
So the way I do it is I do it to give me the bigger rate on top, if that makes sense.
Yeah, you can just do that just to make it better for
Yeah. Yeah, but you could do it whatever way you want. You can pick any. The math will follow actually.
Okay, I like that.
So yeah, it'll work anyway, which is kind of the nice, that's kind of the beauty of it. The algebra, if your algebra is like the steps are good, you can always just rely on it. That's kind of the beauty of it. So okay, but we can look here that the purple CO doubled, but Cl2 was held constant. Okay. Now if we look here, what's the relationship between 1.97 and 3.94? Well, 3.94 divided by 1.97 is equal to 2. So that's also times 2. So if you double something, right, and the reaction rate also doubles, what order would that be?
One.
That would be a first order, right? So then just to kind of show that really quick, I want to use the same equations that I'm going to push this over a bit. Okay. Okay, so then rate 2 over rate 1, we said that's that 3.94 over 1.97, right? And then we're saying, or this is really rate 3 over rate 2, 3.94 over 1.97, and then 0.50 over 0.25. These are both to the m power, right? And then you get 2 here is equal to 2 to the m. And then basically what you're asking is what value of m will make these two sides equal to each other? And then m would have to be equal to 1 in that case. So it must be a first order. Okay. So then my orders are m is equal to 1 for my CO and 3/2 for Cl2. Okay. I know this is a tougher problem, but I think the tougher problems will get you to that level of comfort that you want to be at. Okay. Because that means he can throw any of these problems at you. And I know that you guys will feel good about this. So fortunately, we have another problem here that you can practice, and then another one we're going to work on together, okay? So hopefully after 3 of these problems, you're starting to get the groove, okay? All right, so we'll do that. That's why I kind of rushed through the beginning, because that meant that we can work really slowly on these last 3, okay? Awesome. Oh, look, we have one other person coming. Cool. Okay, so we just found out both orders. We got 3/2 in that. So I'm gonna kind of shrink down all of this work here, or I'm just gonna delete it just so we have some space. Really quick. Okay. So at this point, we now know that our rate law is equal to K, and then that's CO. We just found out that it's to the first power, and we found out that earlier that Cl2 is a 3/2 order. Now, how do I solve for K? Does anybody remember how to do that?
Some algebra to manipulate the concentrations divided by the rate.
Yeah, right. So then I need to I could just solve for K by doing my rate is equal to CO to the first and Cl2 to the 3/2, right? Cool. Awesome. So then I just need numbers to plug into there. And it turns out that you can plug in the numbers from any of these 3 rows. I'm going to pick the first row because it's there and I can plug it in. It's easy. So I'm plugging in the data from that was given to solve for K. Okay. So then what was the rate? It was 0.696, right? And then my CO concentration at that time was 0.25, right? And my Cl2 concentration was 0.80. We can't forget that we're raising that to the 3/2 power. And that will give me my value for K. And I can just punch that in. The answer I got was 3.89. And then if we look, let's see, 3.89, maybe I punched something in wrong. 3/2 power, 0.696, 0.25. Oh, it's 0.40, not 0.80. Sorry. This number here is 0.40. Sorry, I punched that. I don't know why I said 0.80. And if we get that, you get 11. And the only one that really works out for us would be A. That's 11 to get that answer there, okay? kind of a lot of work. I'm sorry, I didn't mean for this to be our first one to be kind of hard, but I feel like it was a lot. It was kind of a really good example that these could be harder than you're led on to believe. Okay. Any questions?
Yeah, the units associated.
Yeah. So let's say we wanted to figure out the units, right? So if we look at the units that they gave us, it's a little interesting that the units are in molar reciprocal. I think it. So let's think about this. So the rate's always molar per second, right? Right. Molar per second, and we found out that CO was first order, so that's molar again. So that's molar per second over molar times molar to the 3/2, right? And then we need to solve for K that way. So then that's molar over molar to the 2/2. You're just essentially adding fractions here, which is 5/2. And then this is 2/2 here, which is how you get that molar to the -3/2 times seconds to the -1. That's how we got that. That's how the units for the molar worked out. Does that make sense? It's kind of fancy. Essentially, what you're doing there is remember that whenever you have x to the a times x to the b is equal to x to the a plus b. So then if you had molarity to the first power times molarity to the 3/2 power, you're essentially adding 3/2 and 1, and that's equal to molarity to the 5/2, because 1 can be represented as 2/2, and you're adding 5/2 there. And then putting that over molarity, well, remembering that another algebra rule, Jesus, I'm sorry about this, over x to the b is equal to x to the a minus b. It's kind of the converse of that, right? So then it's essentially 2/2 minus 5/2, and then you get a -3/2 as a result. Whew. Sorry about the algebra lesson. Yeah. The person left, they're like, I'm out of here. It's too much algebra.
I had to go to work.
Okay, I'm sorry. I'm glad I didn't scare them away. All right. Okay, so let's do 2 more of these practice problems. Okay. If you feel a little spooked out, don't worry. I can't imagine you get a really, really hard one of these. So this is about as hard as it gets, if that makes you feel any better. So let's do it. Okay. Determine the rate law and the value of K for the following reaction using the data provided. Okay. Also, if you want another explanation of that video, I think I have a video with rate laws in the Canvas page where I worked that out also independently, and you can watch me and like how I do it. I do it even slower. So I have like 3 separate videos on doing rate laws. So okay, determine the rate law and the value of K for the following reaction. Okay, so we're given the data. Let's take a look. If we look from we'll call this one 1, 2, and 3. If we look from here to here, it's constant, right? Constant. And then from here to here, 0.3, it's up by a factor of 2, right? That's times 1 times 2. Now, what's the relationship between 2.84 and 1.42? Well, that's double, right? So then if what would be the reaction order for O3 in this case? Can someone tell me? It would be a reaction order of 1, right? Because if you double and the rate doubles, it's directly proportional. So that would mean that it's a first order in this case, right? So then we know that O3 is to the first power. Cool. All right, let's find another equation. We can see here that it's held constant here by a factor of 1. Whereas here, it changed by a factor of what? 2.5. So then let's take a look. What's the relationship between 7.10 and 2.84? So if we divide that, 7.10, divide it by 2.84, what do we get? Fortunately, a sigh of relief, we get 2.5, right? So what's the reaction order for NO2 in this case? Anybody want to give it a shot?
Is it first order?
It's also first order, right? Yeah. That's exactly what I was saying before, that you don't want to get too tied to the idea of it just doubling, right? It's more about if it increases by 2.5 and the rate increases by 2.5, it's directly proportional. And that's how you know it's first order. So then, yeah, that's exactly right. The rate order for NO2 in this, or the reaction order, is 1 as well. Fantastic. So then our rate is equal to K, and it's going to be O3 and O2. And then I'm not going to include the number 1s because it's implied, right? All right. So now that we know that, we could solve for K. Rate over O3 is equal to K. And then we could just plug in some numbers. I'm going to say we're going to pick from one of these. We'll pick the middle one, I guess. And if we do that, what was my rate? 2.84 molar per second. And then we have O3 concentration, 0.66 molar. I can actually omit the brackets. Times 0.10 molar. I feel like I should have started with this one. And then we can solve for K that way. So K is equal to 2.84 over those numbers. Anybody want to take a crack at the units for this? No, it's a little bit tough. So one of the molarities will cancel, and I'll be left with the seconds and the molarity. So then my units are going to be molarity to the -1, seconds to the -1. Alrighty. Then what is my overall rate law? That's going to be that the rate is equal to 43.03 molar -1 times second -1 NO2O3. That is my rate law. And the answer for that one is C. How do you guys feel about that one?
That was way easy.
It was easier than the other one.
Everybody feels a little bit better now, a little more confident on their skills, hopefully. Yeah, I know that, and I definitely didn't know that it was going to be that difficult, so I definitely should have switched the order on that one. Okay, so hopefully that made sense how to do that one. The last one we're going to do is going to be a little bit weird. And hopefully we can recognize why it's more difficult, because that'll allow us to then understand the question even more. Okay. All right, so I want you guys to take maybe a minute to look at the problem and try like tackling it if you can. And then maybe tell me why there might be a barrier, okay? Maybe if someone can identify why it's a harder problem, then that'll make me happy, and then we can work on the problem together, okay? So I'm gonna give you guys a minute, maybe a minute and a half to tell me why this problem is harder than the one before it, okay? So you guys go ahead and give it a go. That feeling when like an Amazon package gets delivered, you're like, yes.
Is it because the equation is not balanced?
Let's see. So the equation is balanced, yeah.
Okay. Okay. Not that. Cool.
Yeah.
Is it because the molarity in I minus doesn't have a constant?
That's exactly right. Yeah, that's exactly right. Yeah. So I think I know exactly what you mean because I know what the answer what I was looking for, but I'll say it for your classmates. So the way we solve this problem typically is that we look for when something is constant, right? For example, here, and then we analyze the other one, right? So it's constant here, times 1, and then times whatever factor there, right? But then if we looked at when we do the other side, we look for when something changes, but we look here and every single one of these changes. It's not held constant for any of them. For any experimental trial, they never held I minus constant, which means that we need to look at this problem with a little more depth, right? Because the last problems we had the ability to kind of look at that. Hey, this was held constant, and then this one was held constant. But now we need to consider more holistically the effects of I minus. So let's do that, okay? So does that make sense, guys? Like what the crux of the problem is on this one?
Yes.
Got it. Okay, cool.
Yeah.
So let's move forward. So by the way, Dr. Fenton told me explicitly to do a problem like this. You did not do one like this in your lecture. So he told me explicitly to do one like this for you. So that's why I'm doing this. I'm not torturing you. So, all right, let's do it. The first part should be normal, right? Let's just figure out the first one that we can solve using the standard methods. Like I said before, we can see here that OCL is held constant here. And we can analyze the effects of I minus then by looking at this one. Now, notice that they also were extra messed up because they normally the reaction the concentrations get bigger going down, but it's actually getting bigger going up this time too. So this is actually times 1, and then going that direction it increased by a factor of 2. You see that? 0.6 is half 0.12. Yeah. So Alex, that's what I was talking about before. They really just kind of change. They can throw the concentrations wherever they want. Yeah. Okay. So 0.06, you multiply that by 2, you get 0.12. So that's why going up, it's a factor of 2 change. So let's figure out the reaction order for I minus, right? And the way we do that is that we can see here, we have to analyze what's the effect on the rate going up that way, right? So the way that we normally do it is we divide the larger number by the smaller number to get some factor. So let's do that. So if we do that, I'm going to do that on the side here. Remember that 7.91 times 10 to the minus 2 is bigger than 3.95 times 10 to the minus 2. And then you don't really have to worry about the 10s to the minus 2s because they'll cancel. So don't even worry about putting those in your calculator. So 7.91, although you could if you want to, it doesn't really matter. If you do 7.91 over 3.95, fortunately, we get 2.0. So that's also a factor of 2. So can somebody tell me what the reaction order of I minus is then?
1.
It's
Yeah.
order, right?
It's also first order, right? Because we've been seeing a lot of first order, right? So if you increase it by that factor, some factor, and the rate also proportionally increases by that factor, first order, right? So boom, we got I minus, it's 1.
Wait, I have a question. Sorry.
Sure, yeah.
So we always compare the second experiment by the first one?
I typically compare the one where the concentration is higher divided by this one that's smaller, because I like getting like numbers that are bigger than one, if that makes sense.
Right, but for example, for iodine, it's 0.060.
Oh, I should probably show how I got that. I did 0.12 over 0.060, and that gave me my 2.
Oh, okay. Okay.
Yeah, that's what I was talking about before. How they
So-
flipped the rows.
Right.
So
Oh, okay.
yeah. So I was doing it. What I was saying before is that I always orient it in a way that I get numbers that I'm comfortable with, not the other way around. You know what I mean?
Right. Okay. So we just kind of rearrange the data
Yeah,
um,
exactly
to
right.
our benefit.
Exactly, yeah. Because
Oh, okay.
otherwise,
Okay. I thought it was like a
yeah.
rule, like.
No, not at all. But if just to kind of like as a thought experiment, if we did that, we would get 1/2, wouldn't we?
Yeah. So
And then
I don't like that.
but here's the thing though. If we went this way though, we'd also get 1/2.
Mm-hmm.
So 1/2, like lowering the concentration by 1/2, if it changes the rate by 1/2, that means it's first order, right? Because
Yes.
it's the same thing. Yeah, cool. So it goes either direction. So, but I know I like being comfortable with multiple 2s, so I'll do that instead. Okay. So then the next step is that we need to then figure out the reaction order for OCl minus. But like I said before, I minus is never held constant, unfortunately. So what we're going to do here is we're going to analyze, let's look at these two then. We'll go from here to here and here to here. Okay, so let's look. So then what's the factor of which I minus is increasing going up? That's by 2. Would you agree?
Yes.
So that's a times 2. And then 0.09 to 0.18, that's also a factor of 2. Would you agree with that? Cool. All right, so then what's the factor of rate increase going up that way? Well, we need to do that math. Let's do that math right there. So then that's 3.95 times 10 to the minus 2 over 9.88 times 10 to the minus 3. And if we do that, we'll get our answer. So the answer I got was 3.999 and so on, right? So we can essentially say that's 4. Would you be okay with that?
Yeah.
Okay. So normally when we do this, if we double the concentration and the reaction order goes up by 4, that would tell us normally that it's a second order. But that's not the case, and we need to also consider the effect of I minus because it was not held constant, right? Okay, so then think about this. If we already know what the effect on the rate would be from this part, what would the effect on the rate be by here? Because we know the order of I minus. If you doubled I minus, what would happen to the rate?
It would double.
It would double, right? So we need to keep that in mind. So then what is the actual effect of doubling this then if the rate went up by 4?
It just doubled.
It also doubled, right? So then if it doubled and the rate doubled, then what's the order of OCl minus?
1.
It's also first order. Does anybody need me to say that again?
Yes.
Okay, so then it's a lot of like mental gymnastics, but it makes sense. Okay, so we found out, maybe I can do it numerically. Let's see. So far we found out that I minus was a first order, right? And we said OCl minus is some order m, and we had it equal to the rate, right? Now, what happened to our rate? Well, from here to here, it went up by a factor of 4, right? All right, by a factor of 4. And then what happened right here? We raised it, we increased the concentration by 2, so there was a times 2 effect here, wasn't already, right? And then we were asking, what's the effect here if the effect here was times 4? Well, then the only answer is that this also must have been a times 2 effect. Does that make sense? And then it must have mean that m must be equal to 1 in this case in order for this to actually be valid. I'm not sure. It's really hard to explain, but it's like a little small little click that needs to happen. Does anybody have any questions about that?
Writing it down like that, I see it.
Yeah, I was just gonna ask, is this true for most of the problems that don't have a constant concentration? Like one of the reactants doesn't have a constant concentration, or it can just vary?
So it really varies. Yeah, sometimes when they're testing your knowledge of if you know how this works, then they'll make it so one of them isn't constant, like because it makes you really think further, right? Um, but yeah, it's really tough. Yeah, it's a tough question. So um,
So this is gonna be on the quiz, that's what you're saying?
yeah, probably. Yeah, probably. Unfortunately, I mean, the fact that he told me to go over it, it's probably going to be on the quiz. He also told me to go over stuff when the rate law is not, it's not 0, 1, or 2, but like some weird number, you know? That's why I'm doing these, yeah. Okay?
Cool, thank you.
Yeah, yeah. So there's the small step you need to consider that the number, the factor by which the rate increased is not only affected by OCl minus, we need to consider the effects of the I minus also. And because it's first order and we doubled it, we would expect to raise the rate by 2. And since it's been raised by a factor of 4, then the contribution of OCl minus must have been 2 also. And if it's 2 and it doubled, then it's also first order. That makes sense. So then now we know our order for that. So I'm going to erase this. So we know part A is equal to rate K, and that's going to be I minus to the first, OCl minus. By the way, you don't need to include that minus, but I just do it just so when I'm explaining it. So now we know our rate law. Part B asks for what's the value of K. And we remember we've done that a bunch of times already where we do the rate over the concentration of I minus in any row is equal to K. And we did that. Let's pick the last column, the last row in this case. Let's pick this guy right here. In that case, you'll get 7.91 times 10 to the minus 2. Remember, that's always molar per second. Over I minus, which is 0.24 molar. And 0.090 molar. Remember, this is kind of the one that we've seen before. So it's a second order overall. So then my answer, when I plug it in, let's see what we get. .662, and then the units is reciprocal molar second minus 1. Oh, by the way, here's like some lingo. Sometimes people will say, instead of saying molar to the minus 1, they'll say reciprocal molar, and that just means m to the minus 1. So like fancy people will say reciprocal molar times reciprocal seconds, like stuff like that. So just so you're familiar. So we now know B, and C. Oh, by the way, for sig figs, it's about 2 sig figs. So it's probably going to be like 3.7 Forgot about sig figs, to be honest. There you go. Just so we round to 2 sig figs, because this has 2 here, and so does this one. Okay, and then C, calculate the initial rate for an experiment where both I and OCl minus are initially present at 0.15. So what would the rate be if we had initial concentrations of 0.15 for both? So we are essentially creating our own column, or excuse me, we're creating a row, right? A row where they're both 0.15 molar, right? And we are predicting this part here, the rate. And we can use the rate law to solve for this, right? We can just say we know that the rate is equal to K times I minus and OCl minus. Therefore, the rate is equal to 3.7 times 0.15 times 0.15. And then we can get our answer. Three molar per second. Whew. How do you guys feel?
Pretty good.
About the rest of you?
That makes sense.
I get it. Yeah.
Cool, I'm glad. Yeah, so we did quite a lot of these, right? But I wanted to really drive the point home that you can see very different variations of this type of problem, right? So you should be able, let's do a recap really quick, right? You should be able to look at the data and give me the rate law, which is the K times the concentrations raised to their orders. And the way we solve for K is by picking some row in our data and plugging that in and solving for K. And then we can actually, because of those numbers that we found, we can actually predict what rates will be because we have all the parameters to solve for that. And that's what we did in part C, right? All right. That was pretty good. How do you guys feel right now? Like mentally, are you guys toast or do you guys feel good?
I think that I'm okay. I actually like the problem where we had the 1/3 or like no
The first one?
yeah, the first problem, the actual harder one, because you explained it way differently than Dr. Fenton, because he doesn't do all of that work when we're in class.
Yeah, he doesn't show the math.
Yeah, and I understand. Like, I feel so bad because he's writing with the actual mouse, and that is
Yeah.
so hard.
I suck with the mouse. Yeah, I can't write with it.
I
Yeah.
can't. He's so good at it though. But anyways, I can see the problem differently even. So I
Cool.
like
I'm glad. Yeah. So I mean, we're definitely like, for the most part, I'm pretty much like on. I like to do the way he does it, but
that.
there are some problems that I do differently just because I find it easier. So that way. But yeah, I'm glad
Also,
that
real
we.
quick, what app
Mhm.
are you using?
This is Notability. Yeah,
Notability. Okay.
it's a really good app. Yeah,
Yeah, I use that one too.
it's honestly the best thing ever. Yeah,
How do
it's.
you put the pins on the side though?
That was a new update actually. I updated the app like yesterday, and it came up with it. Look what
Oh,
they add.
oops.
Yeah, they're called favorites, so you can favorite certain pens. Look at this. They added like little curves you can use and stuff like that. Like sorry, I'm doing a bad job of drawing. It'll like do curves for you now.
Oh.
And they even added like dotted lines and stuff too. Um, yeah.
Okay, I need to update mine.
I know. I'm kind of hyped, to be honest. Okay. So we have about 30 minutes left, and what I wanted to do with that, if you guys feel good, I mean, I don't need this to be a 2-hour session. If you guys only get understanding for an hour and a half. I can always change the times, but we can either go over integrated rate laws together right now in the last 30 minutes, or we can call it and I can answer any questions you guys have right now. I don't want to overwhelm you guys. What do you guys want to do?
I feel like my brain's a little toasty.
I think you're probably not alone. Yeah. Are you guys all toast as well?
Yeah, I think that's a good stopping point. Is maybe go over this stuff again.
Yeah, I feel like I kind of hit you over the head with some rate order stuff, so I
It was
don't want to.
pretty clear though, but
In
I
a
think
good
this
way.
is something, yeah, we need to kind of maybe go over, like rewatch.
Yeah, I'm glad. Yeah, so that's a good stopping point. What we'll do next week, we will work on integrated rate law practice, and we'll do. I'll also tack on whatever material he covers on Thursday. We'll do it like that. So hopefully that'll keep us up to date. And then always I'll keep updating my videos so you can watch those also. But I think that's a pretty good stopping place because yeah, I personally myself, I'm like, oof, that was a lot. So I can only imagine yourself. So I guess on that note, I think we're good. So I'll probably stop recording. Let's see.
I have one question.
Sure.
Can you add for the week one for rate laws? Can you add the concept checks, or maybe I'm not looking in the right place?
Yeah, so those got deleted and I have to rewrite them. Yeah. So
Oh, okay. Oh,
yeah, there was like that huge destruction of our Canvas page yesterday.
oh, okay.
And I guess my concept checks got kind of caught in the crossfire also. So so I'll rewrite those and I'll write them probably tonight.
Okay, it'll be found on the same page on there.
Yep.
I was like, maybe I'm looking in the wrong place or something. But I don't know.
Yeah,
Cool.
it got deleted unfortunately. Alrighty, guys. Thank you so much.
Thanks, Nathan.
See ya.
Bye.
Thank you.
Thank you.